My name is Thomas Mueller. I'm the Director of Applications for the AFM business at Bruker, and I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation today is titled Delivering the Highest Resolution Nanochemical and Property Mapping with the Bruker Inspire. It's presented by Dr. Greg Andreev. Before I introduce Greg, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We will accumulate these questions through the presentation, group them together, and then answer them at the end of the prepared remarks. Quite often, we have more questions than we can answer in the session, and in those cases, we will be sure to follow up with answers via email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within a week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate it if you take the time to complete this, as it helps us pick the topics that are most important to you and to generally make the series better. So let's get started, and let me introduce our presenter, Dr. Greg Andreev. Greg is an applications development scientist and technical lead for near-field optics in the AFM unit of Bruker's nanosurfaces business. He received his PhD from the University of California at San Diego, where he first demonstrated nanoscale imaging of plasmons in graphene. Prior to joining Bruker, Greg was an NSF fellow at the University of Colorado at Boulder. Dr. Andreev is also a co-author on over a dozen peer-reviewed publications and is the primary inventor of several patent-pending technologies in near-field optics. So let me turn it over now to Greg to begin his presentation titled Delivering the Highest Resolution Nanochemical and Property Mapping with the Bruker Inspire. Greg?
Thanks, Thomas, and thank you all for coming to this webinar. And I'm really excited to talk to you about the new product from Bruker called the Inspire. This product is a first-of-its-kind system that enables nanoscale infrared imaging as well as nanomechanical imaging powered by PeakForce Tapping in a new mode which we call PeakForce IR. On this slide, we summarize the capabilities of the Inspire system. In particular, the Inspire is a first-of-its-kind nanoscale mapping system. It allows you to measure chemical, mechanical, and electrical properties at the nanoscale using a combination of exclusive Bruker technologies. In particular, the nanochemical properties are enabled using the technique which we refer to as SPIR. SPIR stands for Scanning Probe Infrared. It is also referred to in literature as scattering SNOM. This is an all-optical method, and in the Inspire, using SPIR, you will be able to obtain both reflection and absorption images with 10 nanometer spatial resolution, which can be up to 1,000 times beyond the diffraction limit, depending on the infrared wavelength you're using. The SPIR imaging capability is also very sensitive to thickness, and the thickness sensitivity can be as good as a single monolayer, depending on the material. The Inspire allows access to a broad range of applications which can be characterized using a combination of these methods. For instance, we will show data from polymer samples, thin film materials, and the ultimate thin film, graphene, and several other examples. The Inspire comes in a very easy-to-use integrated package. There's no additional sample prep required to use the Inspire, nothing beyond conventional AFM sample prep. The optical alignment on the Inspire for the nanochemical imaging is very simple and quick and automated using software. And the results that you get out of the Inspire are meaningful. You will receive reflection and absorption data, which is directly interpretable. Let me briefly show you some data from the Inspire as a sort of snapshot of the Inspire capabilities. On the left side of the screen, you see a series of images which show conventional tapping mode AFM images in height and phase, but also two new channels which are available only on the Inspire, the infrared reflection and the infrared absorption channel. Now the left series of images are obtained at the infrared resonance of this material, the PMMA material, the calculated spectrum of which is shown in the white box here. On resonance, the Inspire shows contrast in both the reflection and the absorption channel. But as you move off resonance, the absorption contrast disappears. However, the reflection contrast remains. We will get into more details on how this works, and I will show another version of this data in the later part of this presentation. As another example of the capabilities offered by Inspire, here is a three-dimensional image where the topography of the image originates from the height channel in the AFM. The color overlay comes from the infrared reflection channel. This sample is a sample of pentacene layers, which is an organic material grown on a silicon oxide film on silicon. So this particular example demonstrates the thickness sensitivity of the optical capabilities of the Inspire. Using the evanescent waves of the SPIR imaging technique, it's possible to have very finely resolved contrasts in individual monolayers of, for instance, pentacene, and as I will show later, graphene layers. And as a last quick example of the Inspire capabilities, we show on this slide a combined imaging mode, which we refer to as PeakForce IR, where it's possible to use Bruker's exclusive PeakForce Tapping technology, which allows nanomechanical mapping, such as what you see here in the first three images. In the middle two images, we see the ability to image the adhesion of the sample and the modulus of the sample with very fine nanoscale resolution. But what's new in the Inspire is the ability to also simultaneously have chemical information. And this comes from the SPIR imaging capability. In this particular example, this is an infrared reflection image obtained at 1900 wave numbers for the infrared frequency. And on the right side of this slide, we'd like to bring your attention to the number of publications already present in literature using the technique of PeakForce tapping. We expect that with the combination of SPIR imaging on the Inspire, PeakForce IR will have even more publications because of the exciting combinations possible of these two techniques. Lastly, as the last part of the introduction, we'd like to bring your attention to the combined possibilities of all of these techniques which are possible on the Inspire. The PeakForce IR technique, which will allow you to obtain the optical images, but also the atomic resolution possible with PeakForce QM, and the electrical imaging capabilities of PeakForce Tuna and PeakForce KPFM. The image in the bottom right is particularly interesting because it is a map of the graphene work function, which was obtained with 20 nanometer resolution and sub 10 millivolt sensitivity in the work function. So now we'll move on to the next section of the talk, where we will introduce the technique and explain how the Inspire is capable of achieving these results. So as a first motivation of explaining the Inspire imaging capabilities, let's first consider an infrared spectrum. This is a typical infrared spectrum that one could get from an FTIR instrument, such as a tensor, for instance, which Bruker also sells. And the way that this spectrum is acquired is by simply shining light through a material and looking at the amount of light that's left over. So by measuring the transmission spectrum, we see the position, the parts of the spectrum which where the energy was absorbed, and we attribute these to absorption by the material. Now the individual lines in this spectrum are actually unique to the molecules which make up this polymer. So for instance, this black arrow is pointing to this carbonyl resonance, and it occurs specifically at this frequency of 1732 wave numbers. Now, if you're not familiar with these units, a wave number is a unit of infrared frequency. It's directly proportional to energy and frequency. 8,000 wave numbers is approximately 1 eV. So such an infrared spectrum provides a chemical fingerprint for a material. So if such a capability existed, if it was possible to take images, for instance, at such a single frequency, like at 1732, well, it would be possible to identify materials that have this particular molecule. And there are two primary limitations with infrared spectroscopy. The spatial resolution is limited to the diffraction limit, which can be around 10 microns, but also there's no simultaneous reflection measurement that's routinely possible. So the Inspire actually overcomes both of these limitations and provides very nice complementary information to what is already available from FTIR. The Inspire will be able to extend the FTIR capabilities by providing infrared images at the nanoscale at specific frequencies. So why should we do nanoscale infrared imaging? Well, as an example of what is already possible, let's consider some research that has been done in this field in academia. So as the first example of how nanoscale infrared imaging is useful, here is a paper from, here is a result from Marcus Raschke's paper in 2005, where he demonstrated 8 nanometer resolution in a block copolymer sample. These individual red regions, these circular regions, are actually the block copolymer regions corresponding to PMMA. These images were obtained on the frequency of the carbonyl resonance, around 1730 wave numbers. But polymers are not the only thing one can study at the nanoscale. It's also interesting to look at semiconductors. Here's a work by Andreas Huber in 2008. This is a very interesting paper because not only did he use infrared light, but he also used terahertz light with the scattering SNOM or SPIR technique. Here, the conventional way to look at such a small semiconducting device, in this particular situation, it's a single transistor, is to use TEM. But TEM requires extensive sample prep, and it also requires a vacuum environment. Scattering SNOM or SPIR does not require such an environment. The imaging can be performed in ambient conditions, and no sample prep is required. So in this example, we can see that SPIR offers additional information that is complementary to what we get from TEM. For instance, the regions that have a large charge density are showing up as very high contrast regions in the infrared channel and in the terahertz channel. As a couple of other examples from a more biological application, I briefly show the very nice result from Marcus Brem in 2006, where a single tobacco mosaic virus was imaged, and where there was clear spectrally dependent contrast demonstrated. And also this unpublished result from my work in grad school, where it's possible to actually resolve the individual nanocrystals which make up the human tooth. Now, all of these examples show that there's quite a bit of information in materials that occurs at the nanoscale, and all of these interesting features have their own infrared, their own responses in the infrared. For instance, this virus has very interesting responses because of its chemistry, and this semiconductor has a nanoscale infrared contrast due to its carrier density. With a conventional infrared microscope, none of these details would be visible. The smallest diffraction limited spot that would be possible in infrared would be roughly the smallest infrared wavelengths that one could use. And if we put such a diffraction limited spot to scale to all of these images, which all have approximately the same scale, we would see that such a diffraction limited spot would take up the entire screen. It would not be possible to resolve any of these features. Now with SPIR imaging, which has nanoscale resolution, such details are clearly visible. So let's go into some details of how SPIR imaging works on the Inspire. So the first part of the Inspire optics is an interferometer, which brings in light from an infrared laser. An infrared laser that operates at a single infrared frequency, which you choose to be in the region of interest that you're perhaps looking at for an absorption line, such as a carbonyl resonance. The light is brought in and focused by a lens onto a metallized AFM tip. The AFM is a sample scanning AFM, which the Inspire has, and it also has a sample engage, which the Inspire also has. The AFM engages the tip and scans the sample in X, Y, and Z. The infrared light focused on the tip creates infrared near fields that exist in the tip sample gap. If the material underneath the tip is more reflecting or less reflecting, it will then interact with these near fields and change the light scattered by the tip. So the next step is that the tip will radiate infrared light, which depends on this near field interaction. This infrared light is at the same frequency that the laser, the same frequency as the infrared laser frequency. This light is collected by the lens, and it's brought back into the interferometer. In the interferometer, the light is, we detect the amplitude and phase of this light using interferometric detection, and we summarize how that works on this next slide. So here we show a diagram that demonstrates how the interferometer operates. So this light that is collected from the tip will go back into this interferometer, where it is combined with the reference field, which is a portion of the infrared laser's radiation that was split off by this beam splitter in the middle. The reference field is, we are able to control the phase difference between the reference field and the light scattered by the tip by actuating a mirror to specific positions. Also, it is important to note that the tip will only scatter back light that is sensitive to the nanoscale information of the sample if the tip is in close vicinity to the sample. So for instance, if the tip is further than about 50 nanometers away from the surface, light scattered from the tip is basically completely background radiation. It is not going to give us any nanoscale information. But as the tip approaches the sample and gets within about 50 nanometers, there is an additional contribution that exists only when the tip is that close. These blue arrows, which we refer to as the near field, E near field, that's the contribution to the detector voltage that we're after. Now, the detector detects a voltage which is proportional to the electric field squared. It's the intensity. But the intensity is composed of the vector sum of all three of these electric fields, which have their own respective phases. And it's that sum squared. So if we, on the next slide, if we look at the bottom portion of the slide, this quantity, if we algebraically expand it, has 6 terms. And it's the first term that we're after in the SPIR imaging mode as implemented on the Inspire. This first term is important because it contains the near field contribution, which contains nanoscale information about the sample, but it also contains a phase difference between the reference field and the near field. By controlling the phase of the reference field by piezo actuating this mirror in the interferometer, we are able to measure the near field phase. And that is what the Inspire does. The Inspire performs 2 sets of measurements at a 0 optical phase and at a pi/2 optical phase. And we refer to these 2 measurements as reflection and absorption. We demonstrate how this sort of measurement is utilized on a specific example. So as we mentioned previously, the PMMA polymer has a relatively strong resonance because of the carbonyl stretch mode at around 17 to 30 wave numbers. On this resonance, the tip will scatter more light than off resonance, as we show on this slide. The near fields are highly sensitive to vibrational resonances directly underneath the tip. And by using the interferometric detection in the Inspire, it's possible to look at this tip scattered light at these different IR frequencies and figure out if the contribution to the light scattered by a tip came from absorption or reflection. And the way that this would work is that on a frequency, for instance, of 1730 wave numbers, when you're on the carbonyl resonance, the light scattered by the tip, which is detected in the out-of-phase channel, will be large. But as you tune off resonance, when our interferometer is aligned to be pi/2 out of phase, the amount of light detected at that optical phase will be quite small. So this is a measurement of the material's absorption, infrared absorption, directly underneath the tip. And it's possible to measure this infrared absorption with 10 nanometer resolution, because that is the radius of the tip. It's the tip radius which determines the extent of confinement for this near-field interaction, just like in this cartoon. And this capability enables nanoscale chemical identification, because polystyrene, as shown here in this diagram, does not have a carbonyl resonance. So it would not, as the sample is scanned to the left, let's say, the polystyrene region would not have any detectable signal in this pi/2 channel, or the absorption channel. Next, it's also possible to look at the reflection channel. The reflection channel behaves slightly differently, as we can see in this calculated spectrum on the bottom. The reflection channel goes up to the left of the resonant and infrared resonance that you're looking at, and then it goes down to the right of it. So at a frequency of 1720 wave numbers, we are to the left of the carbonyl resonance, and we will get a pretty strong infrared reflection signal in the Inspire. But to the right of the resonance at, say, 1760, the reflection, the in-phase signal will be less, and therefore the reflection channel will show a lower signal. However, you might notice that the blue arrows I'm drawing here are bigger than the green arrows off resonance in the previous slide. That's because the reflection channel is almost always non-zero. The absorption channel is 0 if you're away from the resonance. However, the reflection channel almost always shows you something. So although it is perhaps less specific, it is still useful for some applications. It is useful for extracting information beyond chemical identification. You can measure film thickness. You can learn something about your material's conductivity, because the reflection is sensitive to the density of carriers in the material. And you can also study plasmonics, because the infrared radiation is confined to this near-field gap, which is only 10 nanometers, 10 by 10 nanometers. So if the plasmon wavelength is larger than 10 nanometers, it's possible to launch these plasmons in certain materials, such as graphene. Next, I would like to show you some examples of SPIR spectra. So just to showcase the dual capability of reflection and absorption. So for instance, on graphene, there's the reflection and the absorption spectrum are very useful because it's possible to determine the carrier density from these features. On polymers, shown in the bottom left, we already discussed this. It's possible to look at, to identify chemicals by using vibrational resonances. But on thin films, such as thin oxide films of very small thicknesses, it's possible to actually measure the thickness down to 2 nanometers. This is a calculated result from the publication shown in the bottom right here. But this was experimentally verified, and this is some work that I did in grad school. And we were able actually to see a 20% contrast between a 2 nanometer silicon oxide region and silicon. So this method is very sensitive to even the thinnest materials. But the take-home message here is that the ability to measure reflection and absorption simultaneously enables characterization of virtually any material, because pretty much any material will reflect these near fields and will change, and if it absorbs, it will change the phase of the tip scattered light, which we can detect as absorption. In the next section of the talk, we would like to demonstrate these capabilities with some experimental results. As a first demonstration, we would like to showcase the really nice resolution of this technique. Now on this slide, we are showing a calibration grating, which we typically use for calibrating our AFMs. But this grating is also useful for looking at, for instance, the contrast between the silicon dioxide region, which is the square, and the silicon substrate. And also the nanoscale defects or nanoscale inhomogeneities in silicon, which are easily discernible in using SPIR imaging in the Inspire. You can see that as you zoom in to a 250 nanometer image, it's possible to resolve the 10 nanometer gap between these two inhomogeneities. Next, we would like to demonstrate the capability of simultaneous reflection and absorption imaging. We've shown a different view of this data before, but here it is again. So on this sample, we have these PMMA regions, which clearly have a nice absorption contrast in the absorption channel. As we tune off resonance, we see that the absorption channel disappears and the reflection channel remains. And this is a really nice capability because when you first align the system, you might not be near an absorption line on a material that you're unfamiliar with, but you will always get some sort of reflection signal. And you can use this reflection signal to optimize the system and then search for the absorption contrast. Excuse me. Next, we would like to show the combination of SPIR imaging with PeakForce Tapping. This unique combination of nanomechanical and nano-optical characterization is exclusive to the Inspire instrument. Only on the Inspire can you get all of this information simultaneously on the same region with the same AFM tip. This is a great deal of information, quantitative information about your sample. For instance, from the nanomechanical channels in PeakForce Q&M, it's possible to obtain quantitative readouts of the modulus, the adhesion, or deformation, for instance, which give you nanoscale information about the mechanical properties of these different materials. In this particular example, the LDPE, which is the circular region, has a much lower modulus, which is sort of suggested by the name, low-density polyethylene. And in infrared reflection, in this particular example at 1900 wave numbers, we see that it also happens to have a lower infrared reflection, which could be used to measure something about its optical properties at that frequency, for instance, its index of refraction. Next, we demonstrate the capability of the Inspire to measure multiple types of samples. The Inspire is not limited to samples that have to, for instance, expand when infrared radiation is applied to, is focused on them. We do not need any kind of photothermal response. This is an all-optical technique because it measures the reflection of near fields that are in the tip sample gap. So relatively stiff materials such as silicon and silicon dioxide on silicon can be measured with this technique, and even a cross-section of an optical fiber can be measured with very fine details visible in the infrared reflection channel. Furthermore, we can study combined samples that have organic regions and inorganic regions. For instance, in this example in the top right, we have a polystyrene matrix that contains LDPE regions, but also regions where the silicon substrate is visible. And as you might expect, the silicon substrate is more reflective than the organic polymers, and it shows the largest infrared reflection signal. So in this particular example, one could use the infrared reflection channel alone to identify which of these three materials they are looking at. And another nice thing about the Inspire is that one does not have to measure in contact mode. It's possible to measure in tapping mode or in PeakForce tapping mode for studying the most sensitive samples. PeakForce tapping allows you fine control of the interaction forces with the sample down to piconewtons, and it's possible to work with very fragile samples, even powders. As a last example of some experimental results on the Inspire, we would like to now switch over to graphene. So graphene is a very fascinating material. It's a two-dimensional material. It's only one atom thick. It's a one-atom thick layer of carbon. In the infrared region, graphene has a spectrum, a very interesting infrared spectrum, and in the SPIR imaging method, graphene spectrum is even more interesting. Primarily because when one uses near fields that are confined to regions much smaller than the plasmon wavelengths in graphene, one can actually excite plasmons which exist in this lower end and in this lower frequency side of this infrared spectrum. So this lower frequency side where we see this absorption spectrum start to pick up, that's the plasmonic side. And the region to the right of this transition, which occurs at twice the Fermi energy, is the universal conductivity regime. So it's the universal optical conductivity, quote-unquote, regime, where the optical conductivity is constant. So SPIR imaging reveals some interesting information about graphene. For instance, the carrier density can be pulled out of the position of the 2EF feature. The width of this feature could be used to measure the scattering rate and give some information about defects in the conductivity floor of graphene. And the number of layers can also be determined by looking at the level, the universal conductivity level, which would be which one could determine from this reflection and absorption response. As an example of SPIR imaging in the universal conductivity regime, let's take a look at some images obtained at around 1730 wave numbers on a graphene sample. So here's a graphene sample, which is very interesting because it has successive layers of graphene, which starts at a single layer here on the left, if you look at the AFM image, and then it goes to 2 layers, 3 layers, and 4 layers. We also obtained some KPFM data. The KPFM data of this region can be used to estimate the work function, which can be used to estimate the Fermi energy. And as I showed on the previous slide, the Fermi energy would allow us to know the whether we are in the universal conductivity regime or not. Since the KPFM data gave us an idea of the work function of graphene, it was around 50 millivolts, we were able to use an infrared frequency, an appropriate infrared frequency of 1730 wave numbers to ensure that we're in the universal conductivity regime. And the infrared reflection image we obtained on this sample is very interesting because we can clearly discern the individual layers. We can see that the single layer is clearly has a clear contrast with the SiO2 substrate, and the successive layers also have very discernible contrasts relative to each other. So this, for instance, could be, and this data is very reproducible. It is almost always we will see this same profile on graphene flakes that are exfoliated onto silicon dioxide substrates. So this type of SPIR imaging in the universal conductivity regime could, for instance, be used to unambiguously identify single-layer regions. And if we zoom in on this boxed region, we can also obtain a higher resolution image, which shows just how clear the contrast is between just a single layer of carbon and a second layer of carbon added. So this demonstrates that the thickness sensitivity of this technique is sub-nanometer for this particular sample, for graphene. But if we look at this region in a few other imaging modes, for instance, if we look at the nanomechanical properties of this region using PeakForce Q&M, we see that it shows signs of wrinkles. And in the region where the wrinkles appear, we also noticed that the infrared reflection signal is about 2% lower, which is highlighted in this sort of red mask. And this red mask is approximately the left side of these nanomechanical images. The slightly more zoomed out D-band Raman image also shows a slight hint of signal in this region as well. So all of these measurements are consistent with each other. And it seems to suggest that the infrared reflection is useful for detecting regions that have higher defect concentrations. Lastly, let's look at some examples of SPIR images in the plasmonic regime of graphene. That is a very interesting infrared frequency to look for studying graphene. On the left, we show some previously published examples from scientific literature. This is research that I also participated in grad school, and there are several high-profile publications that reproduce these results. And the interesting thing about graphene, looking at graphene at this infrared frequencies in the graphene's plasmonic regime, is that it's actually possible to reflect the plasmons generated by the tip from the graphene interface and have them reflect back to the tip and create a plasmonic interference effect. And we are also able to perform this type of imaging on the Inspire. So for instance, the same sample that I showed you previously in the universal conductivity regime, if you zoom way in on this little corner, it's possible to see plasmons in that corner if you take a high-resolution image. We looked at some other samples as well, which are similar to these triangular shapes published in these very nice papers. The triangular region we have, unfortunately, had a little bit of a fold here and some contamination. But nevertheless, it's possible to see that the plasmons are indeed launched at the interface, and there is some enhancement at the very tip. And this type of data is routine on the Inspire. There's no special tricks involved. Just need the infrared frequency to be tuned to 870 wave numbers with the infrared laser. And such images are possible right out of the box. And lastly, I'd like to end the presentation with another unique capability for plasmonic imaging on graphene. Here in this bottom row, I show 3 images of the same exact region. This is a 1 hertz image, and it goes all the way to 10 hertz. And what's interesting about these 3 images is that the spatial resolution of the plasmonic feature does not degrade as we go to extremely high scan speeds. It's possible to still determine the plasmonic wavelength. The only thing that degrades is the signal to noise. So this is another capability which is unique to Bruker, the ability to perform really fast SPIR imaging. This is perhaps the fastest SPIR image ever recorded. This is a 10 hertz image of a graphene region that's obtained in just 30 seconds. There's no significant loss of spatial resolution, and such an image would be impossible without the stability of a Bruker AFM and the combined near-field imaging approach of the Inspire. And we'd like to conclude the presentation with the summary of the unique capabilities of the Inspire. The Inspire is a first-of-its-kind nanoscale mapping system. It's great for measuring chemical, mechanical, and electrical properties at the nanoscale. It has a broad range of applications, and it's quite easy to use. And we invite you to try it out at one of our demo facilities. And with that, I would like to end the presentation and open it up for questions. And please feel free to contact us at the email addresses listed here if you have if you'd like to get more information about this product.
Okay, thank you very much, Greg. This is Thomas again. I see that we actually got a large number of questions in already. If you can still think of questions, you can also type them in still in the questions dialog box. Let me take a moment to look at the questions, and I'll start to we'll start to answer them. We have about 10 minutes to answer them, so we should get through definitely a few of them, and we'll also follow up with email after. So let me see. So an early question that came in was whether this technique will work with irregular surfaces, say nanoparticles or nano or micron-sized particles. Greg?
Yeah, that's a great question. Micron-sized particles are not a problem as long as it's compatible with AFM imaging. You know, if these particles can be imaged in AFM, then if you can achieve good tracking with AFM, then the infrared imaging capability will also work pretty well on the micron scale. Now, when the particles are smaller, two new things come into play, two new phenomena come into play. So because now the particles might be close to the tip radius, you can't, they will no longer interact with the near fields the same way. So it's as if you're reflecting light off of a ball instead of reflecting light off of a plane. So then the interpretation of the data becomes a little bit more sensitive to the size of these particles. However, the absorption information remains, even though you may be scattering light off of a ball. This sphere or ball will still absorb infrared light, and you'll be able to pick that up in the absorption channel. So, so it's still possible to obtain some useful information that way.
Thanks. And there was another question maybe related. Does the SPIR technique work in contact mode or in tapping mode?
The SPIR technique works in tapping mode as well as PeakForce tapping using interleave. So tapping mode is required in order to modulate the tip sample separation distance in order to modulate the near field contribution to the detector voltage. Now, you don't have to be in tapping mode feedback in order to modulate the distance between the tip and the sample. You could perform a scan using PeakForce tapping to get the sample's topography, lift the tip up, and then modulate the tip up and down, which would therefore modulate the near field interaction. So it's not necessary to use tapping mode feedback. One could use either tapping mode feedback or PeakForce tapping for feedback. And in contact mode, this technique actually doesn't currently work. So it's you would need some way to modulate the tip sample separation. One could perform contact mode first and then switch to tapping mode if contact mode is preferred for the AFM imaging.
Okay, thanks. So that's good. I guess the good thing is that one doesn't need contact mode and it's lateral forces. Also, another question: if the technique is sensitive to one atomic monolayer, how come we don't need a special surface preparation? I think you said no special surface preparation is needed. Wouldn't the results be affected by, for example, an oxide layer on the surface, or say in the case of silicon, or a contamination layer?
Yes, such a layer would slightly change the results, but the layer should be there no matter what. Probably, if it's a water layer, it would exist on one layer of graphene and two layers of graphene, so it just adds a constant offset. What's important is what's underneath those layers. So for instance, if you have successive pentacene layers, like 1, 2, 3, 4 pentacene monolayer, and then some layer of water, well, you can still detect the difference between layer of water plus 1 pentacene monolayer and layer of water plus 2 pentacene monolayers. So if you could have a situation where the surface had an oxide and did not have an oxide, you would be able to detect that as well.
Okay, let's see. Another question on the spectral resolution. What's the spectral resolution of what you showed or what's available with the Inspire?
So in general, it's limited by the accuracy of the frequency specification on the laser. So by specifying the infrared frequency on the infrared laser, you can specify this frequency to 0.01 wave numbers currently in the lasers that we are using, and it's possible that you could go even to even better accuracy wavelength specification. Frequency specification, and then you can take small steps, 0.01 wave number steps, for instance, to obtain SPIR signals at successive steps. So basically the answer is 0.01 wave numbers, because this is the accuracy to which you can specify the IR frequency.
Okay. Another question, what is the limitation for the technique to resolve different materials? Can you differentiate different materials or different material types? You showed, say, polymers, but can you also differentiate other material types from each other?
Well, yes, we can. We showed the ability to differentiate silicon and silicon dioxide, for instance. It's routine to perform such a measurement. It's also possible to differentiate metals from semiconductors. Gold will have a very large contrast with silicon. Also, as I showed in the human tooth example, those are nanocrystals. I believe it's I forget the exact crystal, but it's a calcium-containing crystal which has vibrational resonances around that infrared frequency. And it's possible to differentiate crystal from non-crystal. So pretty much any material that has a significantly different index of refraction, complex valued index of refraction contrast, will show up in this technique. One simply needs to calculate the reflection spectrum, and if the reflection spectrum shows a, let's say, 2% contrast, then it's possible to detect. 1 to 2% is easily achievable with this technique. In absorption, the sensitivity is a little bit less. It's maybe around 5%. But the combination of reflection and absorption together would allow you to unambiguously identify materials with rather small optical contrast.
Good. Another question, actually, on the actually there are two questions that are related. Maybe we can answer both of them. One is the sample depth of penetration. How far down do you probe? The other one is on overall sample thickness. What's the limitation on how thick or thin a sample you can probe?
Well, that's a good question. So the evanescent waves, the near fields that are generated at the apex of the tip, can penetrate 50 to 100 nanometers into the sample. It depends on the sample's optical properties. I mean, if it's a highly absorbing sample, then the evanescent waves will not go as far. And if it's a highly reflecting sample, it may reflect from the first interface, and the remaining evanescent waves might not be enough, might not be detectable anymore as they reflect from the next interface, which may be below the first interface. So really, in general, it's about 50 nanometers. There are papers out there which show gold nanoparticles that are buried in a PMMA matrix, which are, I believe, as far as low as 40 nanometers below the surface, or even 50 nanometers below the surface, and they are still detectable with this technique at the surface level. Now, the second part of the question, sample thickness. You can use all the same samples that you would use in AFM. You do not need to prepare any kind of special slice or like microtome slice or anything like that. The sample is not illuminated from the bottom. The sample is illuminated by the near fields that exist in the tip sample gap. The tip is illuminated by infrared light from the top. And then the tip creates the localized near fields which probe the sample surface. The sensitivity of the technique starts to fall off as the thickness of the sample becomes higher than 100 nanometers, like the thickness of the film, let's say, that you're studying. So you will not see a large difference between a film that's 100 nanometers thick and, say, 300 nanometers thick or larger, because the evanescent waves simply do not penetrate deep enough to reach that second interface at 300 nanometers and then reflect off that second interface and contribute to the tip scattered light. So just think of it as a reflection measurement with an extremely small wavelength, a wavelength that's about 10 nanometers.
I think you answered in passing another question that was on the sample illumination. Is it from above or below?
Yeah, it's from above.
And a question came in early on the detecting differences in doping. I think you showed you can detect differences in doping.
Yes, it depends on the semiconductor, but in silicon, doping levels, I believe it was demonstrated that one could detect the difference between 10 to the 19 and 10 to the 20. We have some results that demonstrate that the sensitivity using infrared lasers can go as low as 5 times 10 to the 18 carrier densities in silicon. We have this data which we could email to the person asking the question. But below 5 times 10 to the 18, it's difficult to do with infrared. That's the reason that Andreas Huber used terahertz light, because that's where the plasma resonance of silicon would be. It would be at much lower frequencies, for which infrared lasers, where infrared lasers do not go. So the Inspire is an infrared instrument, so one would need to measure at terahertz frequencies to get information about, like, let's say 10 to the 17 or low 10 to the 18 carrier densities.
Okay. See, somebody else asking how expensive is this instrument and could it be added to a multi-mode 8? The instrument is really an integrated AFM infrared instrument, but we'll make sure locally we'll follow up with you on the pricing and such. Let's see, we move to the next question. What kind of tips are preferred or are used with this? Can you comment on the type of tips, frequency, coding, etc.?
Yeah, so that's a really nice thing about this technique, is that the tips are already commercially available. There's only 2 specific characteristics that the tip in general needs to have. It needs to have a metallic coating, which is very durable. So for instance, platinum iridium works really well. And it helps if the tip has a visible apex. This greatly increases the amount of scattered light that the optics can collect from the tip. If the tip is not visible apex, then there tends to be an overhang which blocks some of the light from the tip. So those are the only two necessary requirements: a durable metallic coated tip that is visible, that has a visible apex. And these tips are already commercially available. They're not expensive. They're also compatible with PeakForce Tapping and PeakForce KPFM and other electrical modes. So that's the nice thing about having a conducting tip, is you can already perform electrical measurements without having to switch tips. In fact, SPIR, PeakForce Tapping, and PeakForce KPFM can all be performed simultaneously.
Another question somebody's asking, how does SPIR affect the scan rate? How does it compare with your regular AFM scan rate? I think in one of your last slides you made reference to that.
Oh yeah, that's a great question. So the scan rate is only affected if you would like to perform reflection and absorption imaging at the same time. So that will reduce the scan rate by a factor of 2 relative to what you would be doing normally on your AFM. But it does not slow down the scan rate of your AFM. So the optical signals are obtained with sufficient signal to noise to get nice images at standard AFM scan rates. For instance, 1 hertz, 2 hertz, the images look totally fine. And if you look at only one channel, for instance, you look at just the reflection channel, you could even image at 10 hertz, as we demonstrated for the graphene sample.
Thank you, Greg, and actually thank you for the presentation, and thanks to all the participants for taking the time to participate in this webinar. We do have actually many more questions. We will follow up with email to every question. As I mentioned during the introduction, when you get to this to our survey, please do take just a minute to answer our questions. It really helps us to optimize this series. And with that, thank you, everybody, for participating, and hope to see you again in about a month for our next AFM webinar. Thank you.